Thank you. So I would like to thank organizer for this opportunity. So today I'll talk about construction of higher genus Maxface with arbitrarily many catenoid and planar ends. So actually, like minimal surface in R3, these surfaces are zero mean curvature surfaces with space-like surfaces in Lorentz meniscus space. So in few talks, we already saw about what is the Lorentz meniscus space and what is the maximal surface in this Lorentz meniscus space. So I will quickly go through the basic definition of this Lorentz meniscus space and maximal surface in this Lorentz meniscus space. So this Lorentz meniscus space is a vector space R3 equipped with this bilinear form. With this form is defined like any two vector u1, u2, u3 and v1, v2, v3, which defined like u1, v1 plus u2, v2 minus u3, v3. And this bilinear form is called the Lorentzian metric. And in this Lorentz meniscus space, there are three types points. Those points are outside of this double cone, including this origin is called the space-like points, and those points inside of this double cone are called the time-like points, and those points are on this double cone, excluding this origin, as called the light-like points. So in this Lorentz meniscus space, the first Kobayashi defined the maximal surface, which we can represent as a immersion from any Riemann surface to this E13 is called maximal if this immersion is space-like and the mean curvature function is zero everywhere. Space-like means the pullback metric on M is Riemannian metric on whole M. So immersion with space-like with mean curvature zero is called the maximal immersion. And the image of this Riemann surface is called maximal surface in Lorentz meniscus space. And one result proved by Omera and Yamada in 2006 that if we add one condition, extra condition, this completeness, that means if we have a divergent path, then this length of this divergent path is unbounded. So this is the definition of completeness. If we add this completeness, then there is only one example, which is a space-like plane. This is the only one which is complete maximal surface in Lorentz meniscus space. That's why people are interested singularity in this surface because of this Lorentzian nature in this space. So singularity means so those points in the Riemann surface where the pullback matrix vanishes. In other words, we can also say that the immersion is no more space-like at the singularity points. So this is the one of the interesting part of this maximal surface theory, the analysis of the singularities. We'll see which type of singularities in this maximal surface. So, and in literature, this maximal surface with singularities is called the generalized maximal immersion or maximal map. So in this talk, I will discuss about a particular class of this maximal map called Maxface, which contain a special class of singularities called admissible singularities. So any maximal map from M to U13 and Sing X is the singularity set for this maximal map, and any point in the singularity set is called admissible singularities if around this singularity point, singular point, there is a neighborhood U around this P and a function beta, C1 differentiable function beta, so that this beta ds2 defined on this restricted domain extend to a C1 differentiable Riemann metric on whole U. And the differential of this X at this P is not equal to 0, then we call this singularity point as a admissible singularities. So if maximal map contain only admissible singularity point, these are called the Maxface. So this is the one of the subclass of this maximal map. So I am going to construct this type of surface in this presentation. So next is embedded in wider sense. So like in R3, we know that the surface is whole embedded in R3. But in maximal surface case, because of the singularities, we can't say about that the whole surface is embedded in Lorentz meniscus space E13. That's why here Fujimori et al. Defined on weaker condition that called the embedded in the wider sense. That means the surface is embedded outside of some compact set in E13. So let's see few examples, and the first one is maximal catenoid. So these are the complete Maxface with two end. Here there is both end are the catenoid end. This is the catenoid end. This is also catenoid end, and this surface contain the cone-like singularity here. Like this is the maximal helicoid. This is the one periodic maximal surface with helicoidal end, and this is the maximal inner surface. Both are the maximal inner surface, and here this is the singularity set, and this is the one-ended complete Max space, and all the surfaces are the zero genus Max space, and both complete. And this surface is embedded in the wider sense. This is also, but this surface is not embedded in the wider sense. This is only complete Max space. So similarly, the Fujimori et al. Also provide these examples, two examples. The first one, both are the trinoid, but this trinoid contain 3 catenoidal end. So here, this is the one, and second and third, all end are the catenoid end. But in this surface, there is 2 catenoid ends and 1 planar ends. And these both surfaces are the complete Max space. And similarly, George Mix also provided one Max space, which is n number of end. So this is George Mix type Max space, and here this is not complete, only Max space. And this is genus 1, Kim and Young toroidal Max space, and here both ends are the catenoidal end. So this is also 0 genus, but this is 1 genus. So similarly, in higher genus also, there are many authors provided some higher genus case. So in 2006, Kim and Young construct a family of complete maximal map. This is not a class of Max space, only complete maximal map with higher genus, but there is only 2 ends. And this surface having 4G plus 1 swallowtail singularities, and for the genus 1 case, the King and Young provided this example. King and Young toroidal Max space. And then Fujimori et al. Also constructed a higher genus complete Max space. This is about complete maximal map, but this is about complete Max space of higher genus. But this surface having only 2 ends, and genus depends upon the odd case and even case, and all the each member of this family contain same number of swallowtail and cross-pedal cross-cap singularities depend upon their genus case. And in 2024, Bardhan, Biswar and Kumar also gave a existence of new higher genus Max space, but this surface contain only inner type of ends. So from this example, from 0 genus case and higher genus case, one can observe that sometimes the surface is only maximal map, but not Max space, and sometimes the Max space also not complete, and sometimes also we can observe that they are discussed only about at most 2 or 3 ends. So it is natural to ask that, can we construct a Max space that has higher genus and complete and embedded in the wider sense, and this Max space having arbitrary number of ends? So in this talk, I am going to answer this question using one of the technique previously discussed by Martin Trejet in minimal surface case. So before that, how to construct the surface? Already we saw in many talks that there is one representation called the Oester's infer representation to construct this type of surface. So for this representation, we need some ingredient to construct the Max space. So first we need one compact Riemann surface with finite number of punctures, and in this Riemann surface, we need a meromorphic function and one holomorphic one form on this compact Riemann surface with finite puncture, such that this meromorphic function and holomorphic one form satisfy this condition, like 0 divisor of G minus polar divisor of infinite G equal to 0 divisor of DH, and mod G not identically 1 on this Riemann surface, and around any loop, this expression is 0, and real part of this integration ds equal to 0. If we have such data, then this expression will give a Max space. So only we have to choose such data so that we can answer this question, a Max space of higher genus and complete embedded in wider sense, and which Max space having arbitrary number of ends. So, how to construct such data? So here M, G and DS is called the Oester data for the Max space, and the pullback metric in term of this Oester data is expressed like that. And here we know that the singularity set is the zeros of this pullback metric, but because of this condition, though only zeros are mod equal to 1. There is no such zeros of DH. So this is the singularity set for the max space. So our aim is to construct a higher genus max space which look like n number of horizontal plane. Here we have 3 horizontal planes connected by this neck. This is one neck connected by this 2 plane, and in this 2 plane, this is connected by the 5 neck. So we want to construct these type of surfaces, which is complete embedded in the wider sense, and this surface either contain planar end or catenoid end. So main purpose is how to construct this type of surface. So here we use the tracer technique. For this tracer technique, first we need a configuration that will help to construct this type of surface. So what is the configuration? Configuration means we need a neck level, neck position, and neck size. So pictorially one can understand that what is the neck size. This is the neck which lies between first plane and second plane, and this 5 neck lies between second plane and third plane. So this is the second level neck and this is the first level neck. So one can label this as 1,1 means first level and first neck, and this can label by 2,1 second level and second neck. Similarly, this is 2,5 level, that means second level and fifth neck. Similarly, we can assign a point for each neck. That means we assign a complex number P 1,1 for this neck. Similarly, P 2,1 for this neck. Similarly, P 2,5 for this neck. So this is called the limiting position of this neck. Similarly, also we can assign a real number to indicate the logarithm growth of the ends, because this surface either contain planar or catenoid. Planar means if logarithm growth is 0, then the corresponding catenoid will be planar end, and if logarithm growth is non-zero, then the corresponding end will be the catenoid end. So we tuple this coordinate P and Q, capital Q, and refer this as our configuration. And here we define few notation using this configuration. At each neck, we define a force in term of this configuration P and Q. And similarly, this configuration is balanced if at each neck this force is 0, and this configuration is rigid if the differential of this capital F with respect to P has complex rank of n-2. And there is one necessary condition of balance. If configuration is balanced, then this is the necessary condition. So using this configuration balance and rigid, and this differential map Q to W has rank 1, then for sufficiently small t, we have a smooth family of complete max space, and the behavior of this family of surface, if t tends to 0, each member of this family has genus capital N minus capital A plus 1. Here capital N means number of necks, capital L means number of seats, and L number of space-like ends, and whose logarithm growth converges to the QL. So this will decide which type of end, either planar or catenoid. Second, after suitable scaling, we can say that each neck converges to the Lorentzian catenoid, and if t tends to 0, this smooth family look like this surface is converged to a L-seated space-like plane which attached at a singular point PLK. And there is one more condition which telling about the embedded in the wider sense. If the logarithm growth is in the ascending order, strictly ascending order, then we can say that the each member of this family will be embedded in the wider sense for sufficiently small t. So how to construct this type of surface? Here I will give an idea to how to construct a oyster data for this surface. Oyster data means we need a Riemann surface and one holomorphic one from and one meromorphic function. So how to construct a oyster data using the node opening technique? Already we saw in Anu's talk, she constructed a infinite genus and infinite planar end, but this is about the finite case. So how to construct Riemann surface? So one can understand pictorially that suppose we take 3 complex plane, and here take some complex number also. Suppose we attach A1 with B1, and A2 with B2, and A3 with B3, and A4 with B4. Then we have a noded Riemann surface. Then how to open this node? Just remove this inner circle and also around A1, and remove the inner circle around B1. This is the dotted circle, and this is the solid circle, and there is two annulus around A1 and B1, and attach this and both annulus using this relation. Relation is this: suppose we define coordinate chart around ALK. This is around ALK using this meromorphy function, and this is the coordinate chart around BLK. So in this annular region, we add this both annuli using this equivalence relation, VLK and WLK equal to T square. Using this coordinate chart and identification around this point, we can get this as a Riemann surface. And we can add each infinity L, like infinity 1, infinity 2, and infinity L, infinity 3 on each complex plane. This will give a compactification of our Riemann surface of genus capital N minus capital N plus 1, number of neck, number of plane plus 1. So this is about construction of Riemann surface. Then how to construct meromorphy function and one holomorphic one form. So using the coordinate chart here, already we use this GL. Using this meromorphy function, we define our Gauss map. This is our Gauss map when seat is odd or even on the previous Riemann surface. And the next one, there is one big result. Using this result, we can define, and which is unique also, is the meromorphy function on this compact Riemann surface, and this differential form has pole at this end, this puncture, infinity 1 up to infinity L, such that the integration of this one form equal to 2 pi I R1. This is the real positive real number, and the residue of DST at this pole equal to minus Ri. So this is the positive real number which satisfies this relation. So we have here one can notice that from the construction here alpha LK, beta LK, and AI, BI all are the unknown variables here. Similarly in the DH, this is Ri and capital Ri, all are the unknown variables. So we need to find such variables such that this variable, using this variable, the sigma, DST, and G will be the oyster data for our required surface. So next is how to find such unknown variables. So here we use implicit value theorem, and for the implicit value theorem we need one initial condition. So how to find such initial condition? Here we gave a setup using the configuration, because we know that we start with a valence and rigid configuration. So this is the complex quantities. So using this configuration, this is our setup, means this is our initial condition. X0 is our initial condition using configuration. So around this point, we want to find such variables such that this sigma t, gt, and dst will be the oyster data for our requirement. So we already using this implicit value theorem, and also we found these variables such that this will be our required oyster data. That means we already constructed this surface, which having these properties when t tends to 0. So next is which type of singularities this family of surface have. So already we know that mod G equal to one type of points are the singularities of this family. So using this Gauss map is the G. That's why before that we will see one example here. So this is the example of Costa-Hoffmann mix or Costa surface. If M equal to here 2, then this is called the Lorentzian Costa surface, and for the higher M, this is called the Lorentzian Costa-Hoffmann mixed surface. So if L equal to 3 means we have 3-seated complex plane, and in the first level there is one neck, and in the second level there is M number of neck. For example, suppose this is the center neck, this is the one neck, and there is 4 neck. If M equal to 4, then this is the picture for this configuration. If this is the configuration, then we can found this picture. And also this is the neck position in the first seat, and this is the neck position in the second seat, and this is the logarithm growth. So now, what is the singularities? In picture, one can feel that this is like goes to one single point, like cone-like point. But if we zoom this one neck, this is the zoom picture. Actually, this is not goes to just single point. There is many other type singularity also lies in this neck. So how to find? Now we'll see what is the singularities in this neck. So by definition, we know that this is our singularity set. VLK mod equal to T and WLK mod equal to T. And this is and there is this singular set contain different number of connected components depend upon the how many necks in the surface. And there is one function called the governing function defined in term of wasted data GT and DST. We named this as a governing function because this function only give which type of singularities the maximal map have. That's why we call this as a governing function. So using this governing function, if real part of this governing function is non-zero at any singularity point and imaginary part of this governing function non-zero at the singular point, then we call this singularity as the Pedit singularity. And if real part non-zero, imaginary zero, and partial derivative with respect to theta of this imaginary a non-zero, then this singularity is the swallowtail singularities. So here, so the singularity nature of singularity only depend upon the expression of this governing function. Now, what is the expression? Because singularities already we know that the singular set lies in the neck portion of the surface. Already we know also that we know that the local chart around the neck. So how to define this governing function in the neck portion? So how to define? So this is the neck part because we add these two annulus and convert to as a neck. So in this neck, expression of DST, and this is the expression of DST in the coordinate of V, and this is the coordinate of W with this expression. And after few calculation, so we found AT theta as this in term of AN and BN, and using this governing function and one meromorphic function, we define a new function at each neck. At each neck, RLK R theta equal to imaginary part of this quantity, and this will ensure the nature of singularities in the Max space. So from this function, we conclude that whatever surface we constructed above, this singularity set has n singular component. This is the number of neck, and each being the curve around the waist of the neck, and all singularity are the non-degenerate in nature. And if this singular curve mapped to a single point, this is the cone-like singular point. If this is not mapped to a single point, then except some finite singular point, all are the Pedit singularities. And if there is one condition, RLK order of 1 non-zero, then this finite set, the cardinality of this finite set is 4, and this 4, exactly 4 non-Pedit singularities are the swallowtail singularities, and which singularity also lies, that means evenly distributed on the waist of the neck. That means there is not random singularities, they follow some symmetric. We also will see in the example how these swallowtails lies symmetrically in the surface. So here we use this condition, capital RLK1 equal to non-zero. So if this is 0 and some higher order of this capital R non-zero, then we can't say about anything about the singularities. But if we impose some condition, symmetric condition on the configuration, then we can say if there is some higher order term non-zero, then we can say about something about which type of the singularities the maximal map have. Like in this theorem, suppose we assume some configuration, some symmetric in this configuration, and each neck, suppose here we consider one neck, not all neck, just one neck, and in this neck, suppose the R minus 1 order of this R non-zero, then we have 2R number of swallowtail singularities around this neck, considered neck, and this swallowtails evenly distributed when t tends to 0. So let's see in one example. We already saw the configuration for the Lorentzian Costa surface. The configuration for this surface satisfy the symmetry condition. like this is the center neck, and this is the second level neck, and this neck position follow the some symmetry metric. This lies in the unit circle symmetrically. So this is the symmetry configuration. So in this configuration, so we found that R11 equal to this, and for the other neck, because M equal to 2, there is 3 necks. So around each neck, this is the expression. And from the previous theorem, we can conclude that each neck contain 4 swallowtails, and others are the cuspidal singularities. Similarly, for Costa-Hoffman mixed surface, this is the expression for the center neck, and this is the expression for the second level neck. So pictorially, we can conclude that this is the center neck. And for M equal to 4, we have 8 singularities, because 2 into M, so there is 8 swallowtail singularities. The dotted mark are the swallowtail singularities, which are evenly distributed when t tends to 0. And this is the second seated neck. Each contain only 4 swallowtails, and all other solid circle are the cuspidal singularities. So this is the singularity analysis of the whatever we constructed the family of surfaces. So, so this is the references.
Are there any questions?
I have one from online.
Yeah, go ahead.
Yeah, Sai, so the G you took in a particular fashion, right?
Yes,
The
ma'am.
G, the long, yeah, the form of G. So can you change that, or is it for some reason you took it of that form, or the Gauss map? Yes.
Yes, ma'am. So, ma'am, because of the catenoid end and planar end, we need to this type of G,
Okay, I
so
see.
that the surface will be complete and the end will be the catenoid or planar.
Uh-huh. Okay, okay, I see. So there is no other choice.
Yes, ma'am.
Okay. Thank you.
Sorry, maybe you explained this, but you were attaching catenoidal next to the plane, right? So how do you explicitly construct that? So
This surface.
yeah.
That means our setup is like that. Suppose suppose here we have a construction like this. So this is the Riemann surface. Okay, this is the Riemann surface, and we attach here like there is one annulus here around A1 and around B1. We attach, and the Riemann surface is look like this.
Yeah, but how do you explicitly construct it?
The construction of a Riemann surface, or
Yeah, attaching this catenoidal neck.
actually this is the technique from the minimal surface from Trejet. So so surface look like catenoid means if we express this G and DH, this turns out as a so there is oyster data for the catenoidal neck. Like if G equal to Z and DH equal to 1 by Z dZ, this is the oyster data for the catenoid neck. And if T tends to 0, this GST and DST, DST and GT will be converted to the oyster data of catenoid surface. That's why this neck look like a catenoid. This is the behavior when T tends to 0. This is not look like each surface having catenoid neck like in this theorem. So in this theorem, we prove that when T tends to 0, this neck look like Lorentzian catenoid. Not any non-zero T, this is look like Lorentzian catenoid. So when T tends to 0, this DS2 like converts to 1 by Z dZ, and GT converts to Z. And this is the oyster data for the catenoid. That's why when T tends to 0, this surface The neck part look like this surface is converged to Lorentzian catenoid at only that part, not the whole surface.
Okay, yeah, thank you.